Okay, so hello everyone and welcome to the live session number 10 for the week 10 of the NPTEL course Introduction to Semiconductor Devices. The instructor for the course is Professor N.K. Emani of IIT Hyderabad, and I'm your PMRF TA for conducting these live sessions, Samadhan Kamble. I work in CMS experiment at the Large Hadron Collider for my PhD work. So as you know, the plan for these sessions from my side is quite simple. In the first 15 to 20 minutes, I'll briefly discuss the quick recap of the lecture content delivered in this particular week, and then we'll move on to the regular assignment solving, basically from the previous courses offerings as well as the competitive exams. The questions appeared in those particular exams corresponding to this week, of course. So yeah, so without further ado, I think let's get started with the quick review. So in the last week, like the week before this Monday, we have studied the basics of the operations of a Mosfet, that is a metal oxide semiconductor field effect transistor, in which we looked at the saturation, the linear and the subthreshold uh, regimes of the operation, and then we also derived some of the basic expressions of the current as a function of the gate and the drain voltages. So the IV characteristics corresponding to different corresponding to gate as well as the drain voltages. So what we have studied so far till this Monday is what we can say as the classical MOSFETs, in which the simple square law theory holds true. And these were the MOSFETs that were predominantly in use in the 1960s and 70s, and after that there has been a lot of tremendous developments in this particular field. And today, or in this particular week, what we have tried is to basically give you a perspective of what has happened in the last 40 years or so. So after the classical MOSFET picture, in this particular week we are giving a sort of a modern picture of MOSFET and its operation. So let's start with the first slide of the review here. So you can see the first important aspect that we tried to study was the scaling of MOSFET, in which the technology scaling is the main heading, but MOSFET scaling is actually what we have studied, in which what we saw was the lateral as well as the vertical dimensions of the MOSFET were scaled. Not only that, but also the supply and the threshold voltages were scaled by a factor, let's say alpha, which is roughly about 0.7, and also the doping concentration was scaled by this particular parameter. And what we saw is that because of this particular scaling, different parameters are also changing, and essentially what we get is a smaller capacitor, a smaller MOSFET with faster and more power efficient performance. So that is the advantage of scaling. So power dissipation in fact reduces by about 50%. So what happens because of scaling, when you shrink the sizes of the MOSFET, you are first of all making it the MOSFETs making it smaller, right? You are making it faster, and you also making it more power efficient. So these are very good and desirable properties to have. So digital circuit has become much more efficient, and this is the basic reason for the scaling process is being adopted. You can see here this is a particular term we termed it as the technology node. So you can see from 1970s till the 2020 the plot has been adopted. So the technology node is essentially the distance between two MOSFETs. So it is in nanometers, so 3000 nanometer, around 3 micron in 1970s, and each point you can see it has reduced by a factor of 0.7. So each technology node gives us that the distance has been decreased by a factor of 0.7 till this particular point 2020 that I have plotted here. At the same time, if you scale a particular technology and make it smaller, so what happens is we are able to make it more transistors, that is the double the number of transistors for the same power dissipation. So the sizes has reduced, and because we saw that the power dissipation has reduced, the effectively what we can say that is it increases the number of MOSFETs by the same amount. And also this is a classic law, we call it the Moore's law, which which empirically states that for every 2 years the number of transistors on a chip is essentially doubled. So this is what was the famous prediction of Gordon Moore, and what he mentioned is the semiconductor industries tries to keep up with this sort of trend. So even though the effectively now the transistors are definitely not I mean the distance is not about 5 nanometers, it is not true, it is much more complicated than that, but we still use this particular notation and the nomenclature by the Gordon Moore's prediction. So essentially the number of transistors doubles approximately every 2 years is the Moore's law, and we can effectively say that the effective performance of the transistors approximately doubles every 2 years. So this is what is known as the technology scaling, or the Moore's law. So while we do this process, the performance improves significantly, as we have seen, and it turns out that this is not that simple. That is, so there are different various technological challenges, of course, but roughly this is the idea. Also, you can see that the voltages also is scaled by the factor of alpha, but you can see in this particular representation that the supply voltage has not hasn't followed the quite you know linear trend, but still we see kind of a steps in which the voltage, the supply voltage was kept constant for a couple of nodes, and then it was reduced by that particular factor, and this is sometimes called as the classical scaling or the constant field scaling. So there is also a limit of VDD scaling, that is the supply voltage scaling is one of the limitations of the classical scaling, is that it comes from the physical principles that we can analyze. So as I said, to reduce the lateral and vertical dimensions by a factor of alpha, and also to increase the doping concentration, that we can do, but to reduce the supply voltage, which is another property, uh, there is one of the problems. If you change the voltages in every node, then all the peripheral circuits that are to be used, which are the digital chips, also have to be changed, which is not a trivial thing, and it is also not a cost effective thing to do. And that is one of the primary reasons why in 80s and early 90s the voltages are not scaled along with its sizes, and they were kept constant for like couple of nodes and then scaled further. So as I said, the peripheral circuits brings some limitations to the voltage scaling, and also in the recent years, the reasons why the voltage is not scaled is actually has to do with the fundamental physical properties. And as you can see here, one of the like limitation, the property that gives us this limitation is the I on by I off metric. I'm sorry, just a moment. Yeah, so the I on by I off matrix. So once we know that this is I on and this is I off, and this is an important metric for the MOSFET performance, and once we decrease the scaling, that is we make it scaled by the alpha factor, that is 0.7 around, in that case, let us say if this is my second, so if it is scaled, you can see that the I on by I off is reduced, and that is not a desirable property. Also, there is a thing called as the noise margins. So we know that the threshold voltage, if we can consider threshold voltage, if we say the threshold voltage Vt is around 0.5 volt, and whatever is on this side is logic on, that is logic 1, and whatever on the left hand side is logic 0, that is the off state. And this particular margin is important. So if we reduce the VDD below, then the noise margins will be reduced, and that is also not a desirable property for a MOSFET. So one would argue that why can't we decrease the VT? Of course you can decrease the VT, but not beyond certain limit, and then different like limitations and different problems comes into picture. So VT reduction is also not that trivial. So VDD scaling is has some limitations because of these particular metrics. Let us move to the second slide for the summary. Here we saw one important aspect called as the channel length modulation. So we had assumed in the derivation of the ideal current voltage relationship that the channel length L was a constant. However, when the MOSFET is biased in the saturation region, the depletion region at the drain terminal extends laterally into the channel, which reduces the effective channel length. And since the depletion region width is bias dependent, the effective channel length is also bias dependent and is modulated by the drain to source voltage. And this channel length modulation effect is shown in this particular figure here. This is for the N channel MOSFET. Space charge region defined by delta L, as shown in this figure, does not begin to form until VDS is more than VDS saturation. And as a first approximation, we can write that delta L is the total space charge width minus the space charge width that exists when VDS is about VDS saturation. So the delta L is given by this particular relation in terms of different parameters. And since the drain current is inversely proportional to the channel length, that is drain current is inversely proportional to the channel length, we may write ID prime as this particular relation. ID prime is equal to L by L minus delta L times the original drain current, that is ID. Okay, now since ID prime is now a function of the VDS, the output resistance is no longer infinite, and the drain current in the saturation region can be written by this particular relationship here, in which the lambda here is the channel length modulation parameter. So this is an important parameter, and yeah, so this is about the channel length modulation inside the MOSFET. Going to the third and the final slide for the review, that is the recap, in which we saw the variations in the mobility variations that is taken place. So again, in the derivation of the ideal IV relationship, we explicitly assumed that the mobility was a constant. And however, this assumption must be modified for a couple of reasons. The first effect to be considered is the variation in mobility with gate voltage. And the second reason for a mobility variation is that the effective carrier mobility decreases as the carrier approaches the velocity saturation limit. And this effect is discussed here. The inversion layer charge is induced by a vertical electric field, and a positive gate voltage produces a force on the electrons in the inversion layer towards the surface. And as the electrons travel through the channel towards the drain, they are attracted to the surface, but then they are also repelled by the localized Coulombic forces, and this effect is schematically shown in this particular figure here, and this effect is called as the surface scattering. Surface scattering. The surface scattering effect reduces the mobility, and if there is a positive fixed oxide charge uh, near the oxide semiconductor interface, the mobility will be further reduced due to the additional Coulomb interaction. And so the effective mobility is only a function of the electric field at the inversion layer and is independent of the oxide thickness. So this is an important point to note of. The effective mobility may be represented by this particular relation in which uh, the mu naught and E naught are the constants determined from the experimental results. Mu naught and E naught are experimentally determined constants. Okay, so then we move on to different effects because of the short channel, that we have derived the ideal MOSFET relations in the last week, which included the expressions for the threshold voltages and for the current voltage characteristics. We will now consider some of the non-ideal effects, including the channel length modulation that we saw, and additional effects on the threshold voltage occur as the devices shrink in size. A reduction in the channel length increases the trans conductance that we saw in the last week, and also the frequency response of the MOSFET. And a reduction in the channel width increases the packing density in an integrated circuit. So a reduction in either or both of these, channel length and channel width, can affect the threshold voltage. So in particular, if we consider the short channel effect, for the ideal MOSFET, we have derived the threshold voltage using the concept of charge neutrality, in which the sum of the charges in the metal oxide inversion layer and the semiconductor space charge region is 0. We also assumed that the gate area was the same as the active area in the semiconductor, and using the assumption, we have considered only equivalent surface charge densities and neglected any effects on threshold voltages that may occur due to source and drain space charge regions that extend into the active channel region. So effect on threshold voltage because of source and drain space charge regions that we have neglected. So this particular delta Vt is shown here, where delta Vt is nothing but the Vt for short channel and Vt for the long channel. And you can see here that as the channel length decreases, the threshold voltage shifts in the negative direction, so that an N channel MOSFET shifts towards the depletion mode. Okay, so I think this brings me to the end of the short summary, and we can, I think, now move on to the assignment problems. Okay, so this is the question common data for question number 1 to 4. It is as follows. According to the MOSFET scaling proposed by Dennard, choose the correct options with regards to the scaling of the MOSFET parameters. So different parameters, MOSFET parameters that are scaled because of the MOSFET scaling we have to determine. So the first of them is as follows. For a scaling factor alpha, the vertical and the lateral dimensions are scaled as. Okay, so in the definition of the scaling itself, we have said that the vertical and lateral dimensions are scaled by the factor alpha, that is nothing but V and L are reduced by a factor alpha. So the correct option is V is reduced by alpha, V is reduced to alpha V, which is uh, like 0.7 times lesser than the actual V, and similarly the L. Okay, going to the second parameter, that is, for a scaling factor of alpha, the supply voltage VDD and doping concentrations N scale as. So again, in the VDD, we reduce VDD by alpha, and we enhance or increase the doping concentration N by a factor of alpha. So the VDD is reduced by alpha, and the doping concentration is reversed, that is increased by the factor of alpha. So the correct option for this particular question is option D here. Let us move to question 3. Very simple questions. For a scaling factor alpha, the total gate capacitance Cg in farads scales as. So for the gate capacitance, the total gate capacitance, we have the expression for it as total gate capacitance Okay, so the total gate capacitance, as I was writing, can be written as the gate capacitance per unit area, that is C naught, times the total area, that is W times L, that is the our cross sectional area. So we know that C naught, which is our capacitance per unit area, is given by the epsilon oxide by T ox times WL. We know that the thickness of the oxide is also scaled by 0.7, that is by alpha, and these are also scaled by the same factor. So we can write as 1 over 0.7 or 1 over alpha. This is alpha times alpha, alpha gets cancelled. So the total capacitance Cg is also scaled by a factor of alpha. So uh, it reduces by this particular factor, because this particular factor is less than 1. So Cg is reduced, so reduces by around 30% total gate capacitance. If you talk about the capacitance per unit area, that is, if area is you can multiply here, so it is scaled by 1 over alpha, that is, it has increases by a factor of 30%. For the total gate capacitance, that is in farads, it is reduces by factor of alpha. Let us move to question number 4, which is also based on the common data. The question is as follows: for a scaling factor, again alpha, the delay in the circuit, that is TD, scales as. So again, for the T delay, we have the expression which is CV times the current, and we saw that our capacitance scales by the factor alpha, also the voltage is scaled by factor alpha, and also the current scaled by factor alpha. So alpha gets cancelled. So T delay scales by a factor of alpha. In our case, alpha is less than 1, so it reduces by around 30%. So TD reduces by around 30%. So the correct answer is TD this. Okay, so the questions from the common data are over now. I think we will move to the next question then, question number 5. So the objective of the question is as follows: determine the increase in drain current due to short channel modulation. So the question, I'll read it for you. Consider an n-channel Mosfet with a substrate doping concentration Na given by this particular figure, and a threshold voltage of 0.4 volt and a channel length L of 1 micron. The device is biased with VGS of 1 volt and VDS of 2.5 volt. Determine the ratio of actual drain current compared to the ideal value. Okay, so ID prime by ID is what they have asked. ID prime by ID is the thing that we have to determine. So for that, we know that the expression that we have shown in the summary slide here is that ID prime is nothing but L by L minus delta L, times the actual ID. So we need to determine delta L first. We can use this particular expression for that. So again, we need different parameters to be put in the expression for delta L. So let us first find out those parameters. One of them is the phi fp, and we know that the phi fp is given by Vt ln of Na by Ni. So in our case, Vt is 0.0259 times ln of Na is 2 times 10 to the power 16 divided by Ni, which is given by 1.5 times 10 to the power 10 centimeters cube per centimeter cube. So we'll get the value of phi fp as 0.36 volt. So this is one of the parameters. Similarly, we need VDS saturation, and we know that the VDS saturation is given by VGS minus VT. In our case, VGS is 1 and VT is 0.4. So 1 minus 0.4, that is 0.6 volt. So the second parameter is also determined. Now let us find out the third parameter, that is delta VDS, and this is given by VDS minus VDS saturation. So VDS is 2.5 volt, 2.5 minus VDS saturation is 0.6 that we determined. So it will give us the delta VDS of 1.9 volt. Okay, now I think we have sufficient information to put in our delta L expression. So our delta L is given by 2 times epsilon for the semiconductor times the electronic charge times the doping concentration times square root of phi fp plus VDS saturation plus delta VDS minus phi fp plus VDS saturation. Okay, so now this is just mere substitution. Now we have different parameters and we can substitute it and we'll get. Okay, so one more thing is epsilon s is for silicon, it is 11.8, 11.7 indeed. So if you just substitute all these parameters, epsilon s, the electronic charge, we'll get the value of delta L as 1.8 times 10 to the power minus 5 centimeter, which is nothing but 0.18 micrometer. Okay, now we have delta L, so we can find out ID prime by ID, which is given by L over L minus delta L. So L in our case is 1 micron. So 1 micron divided by 1 minus 0.8 micron. This will give the ratio of ID prime by ID as 1.22. So this is our final answer. So one thing to note here is that the actual drain current increases as the effective channel length decreases when the transistor is biased in the saturation region. So the factor more than 1 tells us this particular thing. Okay, so let us move to question number 6 then. Okay, so this is again a conceptual question. Given below are two statements regarding the current in a short channel MOSFET. So the first statement is the current for a short channel MOSFET saturates at a larger VDS as compared to long channel MOSFET, and the second statement is that the short channel MOSFET reaches the critical field at smaller applied biases leading to velocity saturation. So this has been discussed quite in detail in the class. So if you just go back to the question, this statement one again, the current for a short channel MOSFET saturates at a larger VDS compared to the long channel MOSFET. If you just draw the current versus VDS curve for two MOSFETs, we have shown that for the short channel MOSFET, the saturation happens at the lower VDS. It saturates at lower VDS as compared to the long channel MOSFET. So this particular statement is the false here, and the second statement is that the short channel MOSFET reaches the critical short channel MOSFET reaches the critical field at smaller applied biases, leading to the velocity saturation. And this indeed is correct, as we saw that the the velocity saturates, the velocity, that is feed drift, saturates because of the at a particular field called as the critical field, corresponds to E critical. And we saw that for the short channel, E critical is the electric field is around close to the E critical value. So the short channel MOSFET reaches the critical field at smaller applied biases compared to the long channel MOSFET, and hence it leads to the velocity saturation. So the first statement is false and the second is true. So the option B is the correct option. Moving to the question number 7, it is again a common data question. Okay, so the figure 1, it is a characteristic curves for the drain current versus VDS for two MOSFETs having different lengths. So for the different channel lengths is shown, is plotted here. VGS in this case is kept constant at 1.8 volt. The W by L ratio for both MOSFET is also kept constant, and answer the following questions based on the given data. Okay, so the question number 7, which is the first question based on this data, is as follows. Identify the type of MOSFET corresponding to the curves in the figure. So as I have discussed in the previous question as well, that for the shorter channel, the VDS saturation is lesser than for the VDS saturation for the long channel. So in this particular diagram, we can see that this particular characteristic corresponds to short channel and this corresponds to long channel. So the characteristic tells us this quite in detail. So the answer is MOSFET 1 is long channel and MOSFET 2 is the short channel. Okay, so let's move to question number 8 then. Question 8 is as follows. Choose the correct option or options with regards to the critical electric field EC at which the velocity saturation occurs in a short channel MOSFET. So if you just plot the drift velocity versus the electric field in volt per centimeter, we have shown that ideally we have a linear relationship, but at a particular electric field, say a critical electric field, the drift velocity actually saturates and attains a saturated value called as VD saturation. This is VD saturation. So this is a particular EC. Now they have asked it for two different channels, short and long channel, and this particular EC is around 10 to the power 4 to 10 to the power 5 volt per centimeter generally. And if you go into this particular characteristic curve, you would see here that the electric field for, let's say, the long channel, electric field for the long channel is the VDS, that is 1.8 volt, divided by the channel length, if we consider a channel length of say 10 times 10 to the power minus 4 centimeter, you will see that it is the electric field is around 10 to the power 3 volt per centimeter, which is less than the critical value. Similarly, for the short channel, when we decrease this particular length, the electric field would be increased and it will be roughly equal to our critical field, electric critical field, and hence the drift velocity saturation occurs at the lower electric field in the short channel. And indeed we have the answer here, that the electric field across the channel for MOSFET 1, which is the long channel, is less than the critical value, and electric field across the channel of MOSFET 2, which is the short channel, is more than the critical, more than or equal to, this has to be done, more than or equal to of the critical electric field. Going to the question number 9, the second last question, the approximate VD saturation for the MOSFETs is. So again, if you go for the MOSFET number 1, that is the long channel, we can see that the VD saturation is roughly given as VDS minus VT. So 1.8 minus VT is around 0.5, so around 1 or 1.2 is the VD saturation for the long channel, and for the short channel it is around 0.4 to 0.5. So in our options we can say that the for MOSFET 1, which is the long channel MOSFET, VD saturation is around 1 volt, and for the MOSFET 2, which is a short channel MOSFET, VD saturation is around 0.4 volt. Simple observation. Going to the last question for this particular session. This is a calculation based question. I'll read out the question for you. Calculate the threshold voltage. Calculate this threshold voltage shift due to short channel effects. So this is for the short channel effect that I have mentioned in the summary slide. So the question is, consider an n channel MOSFET with the doping concentration of 3 times 10 to the power 16 per centimeter cube, and the length of the channel as 1 micron, Rj, which is a parameter, a depth parameter of 0.3 micron, and the oxide thickness of 20 nanometer, which is 200 angstrom. Okay, so we need to calculate the threshold voltage shift. Okay, so I have shown that expression for the threshold voltage shift in the summary slide. This is the particular expression. So this particular expression we can use to determine delta Vt. So, however, before that we need again few parameters to be determined. So let us find out those first. So first of them is the oxide capacitance, that is Cox, which is nothing but the epsilon ox by the T ox. If you just substitute it, we'll get epsilon oxide is around 3.9 times the 8.85 times 10 to the power minus 12 divided by the thickness, which is 200 angstrom, that is 10 to the power minus 8 centimeters. So Cox is nothing but 1.7 times 10 to the power minus 7 farad per centimeter squared. So one parameter is determined. Again, the second parameter is nothing but the phi fp, which is given by Vt ln of Na by Ni. So I don't need to substitute it. I'll finally write phi fp as 0.37 volt. So these two parameters are determined now. Now one more parameter, that is x dt, is to be determined in order to find out delta Vt, and this parameter is given by 4 times epsilon s phi fp over electronic charge times the doping concentration. epsilon s is 11.7, so 4 times 11.7 times 8.85 times 10 to the power minus 12 times phi fq that we have determined as 0.37 divided by the electronic charge 1.6 times 10 to the power minus 19 times the concentration of 3 times 10 to the power 16. If we just calculate it, we'll get the value of x dt as 0.18 times 10 to the power minus 4 centimeter, which is nothing but again 0.18 micron. Okay, now we have the parameters. We can substitute in the expression of Vt, delta Vt indeed, and that is as follows. Delta Vt is nothing but minus of E Na x dt over C ox times Rj over the length, the channel length, times under root 1 plus twice x dt over Rj minus 1. Its derivation is given in the Niemann's book quite nicely. You can refer it later on. So if you just substitute all these parameters that we have determined, we'll get the value of delta Vt simply as minus 0.0726 volt. Okay, so one thing to note here is that if the design value of the threshold voltage of an N channel MOSFET is to be let's say Vt of 0.35 volt, so for example a shift of this much, that is minus 0.07 volt, due to the short channel effect is quite significant, and it needs to be taken into account while designing the threshold voltage for an MOSFET. Okay, so this is an important point to be noted. And as we have like few minutes, I'll just go to the bonus question and I'll end then. Okay, so the question is as follows. In the year 2007, we saw that the high-k dielectrics were introduced, so in the 45 nanometer technology, and this was primarily for what reason is the question. So we saw that reducing the thickness of the oxide, like T-ox reduction, was a trend, so that we could get better capacitance. So C ox, which is inversely proportional to the T-ox, but there is a physical limit to it because of a phenomenon called as the quantum tunneling. And as we reduce the thickness further, the quantum tunneling would occur and the leakage of the charge carriers would take place, and that is not at all desirable. So in order to increase the capacitance and increase the performance, what we indeed used was the high-k dielectrics, so in which we saw that the effective oxide thickness is also reduced. Even if you don't physically reduce the thickness, because we are using high-k dielectrics, effectively we can say that the thickness of the oxide is reduced. So this is effective oxide thickness, and so high-k dielectrics were introduced to reduce the gate leakage current due to tunneling, and also to improve the performance of the capacitors and the MOSFETs that were introduced in the 2007. Okay, so I think this is what I had planned to like cover today. I think this brings me to my final slide. Do you have any question?
Thank you, sir.
Okay, thank you. And with this, I would like to thank you all for joining for this particular live session. And I hope to see you in the next live session, that is live session number 11 for the week 11 of the course Introduction to Semiconductor Devices, scheduled on the 7th of October at 6 p.m. Friday. So meanwhile, as I always said, that you can go on to the NPTEL course site and ask your questions on the discussion forums. Also, the recordings of these live sessions will be uploaded to my YouTube channel, and you can also go back and refer them. So that's it from my side, and I hope to see you in the next live session.